learn about interpretation and properties of the wave function. First we see the concept of a state function or the wave function. The concept of state function is unique to quantum mechanics. The mathematical function defined for the system is known as the state function or the wave function of the system. The function is defined for all variables of the system, including time. Being a mathematical function, it may be contain real numbers or complex numbers. Accordingly, the function may be defined as real function or the complex one. The state function so defined will be used in association with the Schrödinger wave equation. Hence, the function must fulfill certain conditions mathematically. The function should be finite, single-valued, and the continuous. Finite it is irrespective of the actual value of its variable. The function must always give a finite value. Even if the variable tends to become infinite, the value of the function should remain finite. Single-valued, for a given value of the variable, the value of the function should be 1 and only 1. Continuous is there. The Schrödinger equation is a second order differential equation. The second derivative of a state function must be well defined. We can take a second derivative of any function only if it is continuous. There is no inflex sign in the curve. And if its first derivative, that is its slope, is continuous. The wave function psi in this Schrödinger equation is a function of a position only, and independent of a time. It may be a complex function or a real one. For the complex function, psi takes the form psi is equal to small a plus small I small b. Psi is equal to a plus ib, where a and b are real functions of the coordinates and I is equal to a square root of a minus 1. The complex conjugate of psi is psi star is equal to a minus ib. Psi into psi star is equal to a square plus b square. Thus the product psi into psi star is always real and not a negative quantity. If psi is a real function, the psi is equal to psi star. Hence psi into psi star is also equal to psi square of a psi function. According to the Max Born, the sec square of the wave function r psi is equal to psi star at a point is proportional to the probability finding the particle at that point. The square of the wave function r psi into psi star represents the probability density. That is, it is a measure of the probability of finding the particle, that is electron, at that point for a particle to move in 3 dimensions. The wave function depends on the point r with the coordinates x, y and z. In such a case, the probability of finding the particle in imperceptible value d tau is equal to dx into dy into dz at the point r is proportional to psi into psi star d tau. The sign of the wave function has no significance, but its square is physically important. The wave function which satisfies the above condition is called well-behaved function. The wave function contains all the dynamic variables of the system and it carries information about the location of the particle. In Schrödinger wave mechanics, the square of the wave function represents the probability of finding a particle, that is electron, at that point. If the wave function of a particle, that is electron, has the value psi at some point x, then the probability of finding of the particle electron between x and x plus dx is proportional to psi square dx. The square of modulus of a wave function is a probability density, and to find the probability it must be multiplied by the length of the very small region dx. The probability distribution function will be psi square into dx, definite volume dx. This will be considered as a measure of the amount of electronic charge per unit space for a three-dimensionally moving particle like the electron. If the wave function has the value psi at some point r, then the probability of finding the electron in an extremely small volume d tau. D tau is a small volume in a three-coordinate space dx, dy, dz. The psi square dx is equal to psi into psi star. The modulus psi square dx, dy, dz. If modulus psi square is real and never negative, the total probability in the available space is a unity. A integration b modulus psi square dx is equal to probability in bracket a less than or equal x less than or equal b minus infinity integration to plus infinity, then modulus psi square dx is equal to 1 for one dimension. Probability psi square dx of finding the particle in all the infinitesimal region lying between a and b, small a and b. A probability of 1 represent certainty, since it is certain that a particle is somewhere on the x-axis. The minus infinity, that is the limit minus infinity to plus infinity psi square d tau. Psi must be finite and single valued for all the values of the coordinates. Psi must be continuous function of the coordinates. Integration psi square d tau must be finite when the integration is carried out over the whole space. A single value means although the probability density is finite, it cannot be infinite at any point, only one value at each point of a space. Second derivative of psi must be well defined. We can take a second derivative of any function only if its first derivative, that is its slope, is continuous. Wave function psi cannot be zero everywhere because the particle describes somewhere. The wave function must be single value and finite between the limits x is equal to 0 to x is equal to a. The wave functions which satisfy the following conditions are acceptable. Psi must be finite and single valued for all value of the coordinates. This means that the probability density of particle at a point x, y, z in a space must be unique. It cannot be infinite at any point, otherwise the probability density must be infinite. Psi and its first derivative must be continuous. The requirement of a continuous implies that there must not exist any sudden changes in psi when variables are changed. Then the limit minus infinity to plus infinity psi star into psi d tau, or minus infinity to plus infinity limit psi square d tau, that is the limits minus infinity to plus infinity psi square d tau must be finite when the integration is carried over the whole space. A wave function which satisfies the above conditions is known as well-behaved function. Thank you.